JWST isn't just giving us prettier pictures of space. It's upgrading the quality of the evidence. And when evidence gets sharper, two things happen. Some old ideas grow stronger, and a few chapters of the story suddenly look unfinished. Here's what might make you pause. What if the universe's first pages weren't as slow and orderly as our textbook said? What if JWST is revealing a faster, more intense opening act? In the next few minutes, I'll walk you through 3 JWST mysteries that are making scientists rethink the early cosmos. Each points to the same intriguing question. Did the universe follow the script? Or did it cook faster than we imagined? Mystery 1. Galaxies that are too big, too bright, too early. Mystery 2. Dust and complex chemistry appearing ahead of schedule. Mystery 3. Strange light patterns and objects that trigger double-check moments in research labs. Let's start with the most visually striking puzzle. Galaxies that seem to have grown up too fast. In the standard story of cosmic evolution, the early universe starts with tiny, fragile structures. Over billions of years, gravity pulls matter together, slowly building larger and larger galaxies. You don't expect to find massive, mature-looking galaxies in the universe's toddler years. But JWST's deep field images are telling a different story. They reveal galaxies that look surprisingly grown up at redshifts that correspond to just 300 to 500 million years after Big Bang. These galaxies appear large, bright, and structurally complex. Features that, according to earlier models, should have taken much longer to develop. So what's going on? If these galaxies are truly as massive and evolved as they appear, it suggests that star formation in the early cosmos might have been incredibly efficient. Or perhaps our methods for estimating their masses and distances need refinement. Or maybe both. A key nuance here. In astronomy, bright doesn't always mean big. A galaxy can appear luminous because it's undergoing a burst of star formation, or because interstellar dust is reflecting light in unexpected ways, or because gravitational lensing, a natural magnifying effect caused by foreground galaxy clusters, is amplifying its image. So the real question isn't whether physics is broken. It's what specific processes made these galaxies look so mature so soon. Several hypotheses are on the table. Early star formation might have been more intense than models predicted, with gas converting into stars at remarkably high rates. The first generations of stars might have had different chemical compositions, affecting how their light is interpreted today. Or we could be witnessing these galaxies through cosmic lenses, magnified by the gravitational fields of massive clusters in the foreground. Why is this still an open mystery? Because JWST isn't showing just 1 or 2 outliers. It's revealing dozens of candidates that shift the conversation from, is this a fluke, to, is this a new pattern? And if it is a pattern, it might mean the early universe was more energetic and dynamic than we ever anticipated. Before we move to the second mystery, let's pause for a reality check. This is how science evolves. A new instrument reveals data that doesn't quite fit. Then, through careful analysis and debate, our models adjust. That's not a sign of crisis. It's a sound of discovery and progress. Mystery 2. Dust and chemistry. Why so early? Cosmic dust isn't just space dirt. It's stardust, forged in the hearts of stars and scattered across the cosmos by supernovae and stellar winds. Dust grains are also the building blocks of complex molecules, making them key indicators of chemical evolution. In a traditional timeline, the first galaxy should have been relatively pristine, dominated by hydrogen and helium, with only traces of heavier elements. Dust and complex chemistry should emerge gradually over many generations of stars. But JWST's infrared eyes are telling a more hurried story. In some of the earliest galaxies observed, spectroscopic data reveals strong signatures of dust and molecules like carbon monoxide and water ice, chemical complexity that seems to appear surprisingly early. Does this mean the universe's chemical kitchen was already busy cooking sooner than expected? Not necessarily. But it does suggest we may have underestimated the pace of early enrichment. Perhaps the first stars polluted their surroundings with heavy elements faster than models predicted. Or maybe early galaxies experienced intense, short-lived bursts of star formation, rapidly producing and dispersing dust. Another possibility. Our interpretation of the data could be influenced by how dust and gas interact with light across cosmic distances. Factors like redshift and interstellar extinction can affect what we detect and how we interpret it. Think of it like entering a bakery and smelling fresh bread. You might assume the ovens have been on for hours, but maybe they're just extremely efficient, producing the same aroma in a fraction of time. JWST gives us the scent of cosmic chemistry with unprecedented sensitivity. Now the challenge is to determine the recipe and timing behind it. Mystery 3. Weird light, strange shapes, and the need to double check. One of JWST's most fascinating capabilities is its ability to peer through galaxy clusters, which act as natural gravitational telescopes. The immense mass of these clusters bends space-time, magnifying and distorting the light of background objects, an effect called strong gravitational lensing. This lensing can produce dramatic arcs, duplicate images in stretched or warped shapes. While it's a powerful tool for observing faint, distant galaxies, it also complicates interpretation. A small, faint galaxy can appear large and bright if highly magnified. So when JWST detects an object that looks bizarrely luminous or oddly shaped, the first question is always, is this truly extraordinary or is it just lensed? Even after accounting for lensing, some detections remain puzzling. Certain objects exhibit light patterns, colors, or structural features that don't align neatly with current models of galaxy formation or active galactic nuclei. These aren't breakthrough or bust moments. They're invitations to look closer. This is where the real scientific process unfolds, not in dramatic headlines, but in careful re-examination of data, calibration checks, and iterative modeling. When scientists say we need to double check, it's not an admission of uncertainty. It's a commitment to rigor. So where does this leave us? JWST is painting a picture of the early universe that is richer, more complex, and perhaps more hurried than we once imagined. The emerging hints suggest large structures may have assembled more rapidly. Chemical enrichment and dust production might have begun earlier. The diversity of early objects may be greater than predicted. These aren't revolutions, they're refinements. Each mystery drives better observations, sharper models, and deeper understanding. How will these puzzles be solved? Through more data, deeper surveys, sharper spectroscopy, improved lensing models, and time, both telescope time and cosmic time, as JWST continues to observe. And through collaboration, missions like the upcoming Nancy Grace Roman Space Telescope and ALMA's millimeter wave observations will complement JWST, building a multi-wavelength understanding of cosmic dawn. Sources: NASA JWST Early Release Science Programs, Foundational Data on High Redshift Galaxy Candidates, the CRS Cosmic Evolution Early Release Science, Survey, Key Findings on Galaxy Growth and Morphology in the Early Universe, JWST Advanced Deep Extragalactic Survey, Spectroscopy-Driven Insights into Early Chemical Enrichment and Stellar Populations. Detailed references and links are available in the description. Every claim is traceable to published data or peer-reviewed work. This isn't speculation, it's science in motion. Stay aware, stay adaptable, stay curious. Now, I'd like to hear your thoughts. Which of these three mysteries do you think will be solved first? Keycap 1, Too Early Massive Galaxies. Keycap 2, Early Dust and Chemistry. Keycap 3, Strange Lens Objects. Drop number 1, number 2, or number 3 in the comments. I'll create a dedicated follow-up video explaining the winning topic in greater depth. Let me know which